thank you very much to the organizers, and congratulations to Michel for his birthday, even though we were 2 years late. So this conference is about non-commutative algebraic geometry. And I feel I came to appreciate the subject quite late. I feel like somehow I only barely belong. I should have, yes. So maybe I should explain it by saying that I was a student of David Mumford's, and my view of algebraic geometry was somewhat shaped by what I learned as a graduate student. And very early in my career, so in early 1981, I was just a second-year grad student, and Mumford gave a course on modular. And during his course, he introduced geometric invariant theory, and he said, well, look, in the world of algebraic stacks, every moduli problem is solvable. But who cares? In algebraic geometry, so, so of algebraic geometry, you care about projective rates. That's what's the of the field. It's what you want to study. Now, in order to study it, you introduce schemes. And if you're really brave, you introduce stacks. Algebraic geometry is really the study of projective variety. Rest is fluff. So,
yeah, it's not your fault.
Yeah, it's okay. So in the world of algebraic geometry, projective varieties are the center, the rest is fluff, and I need hardly say what Mumford's view of non-commutative algebraic geometry would be. Okay, I'm not David Mumford, and my views on algebraic geometry and on mathematics are different from his. In fact, every time I see him, he tells me that my work is far too abstract and I should work on applications much more. But that said, I came to appreciate non-commutative geometry late. And the two papers that really struck me as amazing, the first, well, yes.
Yeah, this should be, maybe you have to keep it.
Okay. The two papers that really amazed me are these two. And what's striking about them, okay, so the first paper says that there are all of these constraints. So the Olaf paper about smooth and proper schemes. It says that all of these wonderful constructions in non-commutative algebraic geometry, you can look at non-commutative resolutions, you can glue non-commutative schemes, you can do wonderful things. But if you start with smooth projective varieties, if you start with the boundary-derived categories of coherent sheaves with admissible subcategories of boundary-derived categories of coherent sheaves, you never leave this world. All of these constructions end up with admissible subcategories. So you might think that if you accept that admissible subcategories of boundary-derived categories of coherent sheaves are interesting, then all of the other constructions are interesting. And the second theorem is this theorem of Vandenberg, of Rizzardo and Vandenberg. And what's amazing about it is, well, look, we all care about Fourier-Mukai transforms. They have nothing to do with the non-commutative worlds. They tell you about how to go from boundary-derived category of coherent sheaves on one scheme to boundary-derived category of coherent sheaves on another. And it's interesting to know that there are non-Fourier-Mukai transforms. And okay, so this is a theorem with nothing to do with non-commutative algebraic geometry, but the proof, the construction of Rizzardo and Vandenberg is by way of A infinity deformations of a commutative algebraic variety. I mean, I need hardly tell you what Mumford would have to say about A infinity deformations of smooth projective varieties, but what can you say? They're essential to the proof. So it is an amazing paper for various reasons, but since in order to convince a skeptic that the subject is interesting, the best way is to take something that they care about, something they want to know, and prove it by your methods. Let me focus this talk on that. So the center of the talk will be a theorem about boundary-derived categories of projective varieties, but the proof will be using non-commutative methods, and in particular, it'll be using the non-commutative methods introduced by van den Bergh. So, okay, let me say a little more about the work that made me appreciate non-commutative geometry. So first of all, also in the list of papers should be the one by Bondel and van den Bergh from the early 2000s. It took me a while to appreciate just how important this paper is, but as we'll see later in the talk, it influenced my work a lot. And finally, okay. I should say a tiny bit more about this paper because it will play no role in the rest of the talk. So, as I said, this paper produces a non-Fourier Mukai functor by using an A infinity thickening of a smooth projective variety. And then it somehow cleverly constructs a non-Fourier Mukai, it constructs a triangulated functor between the derived category of the ordinary projective variety and the derived category of its Fourier Mukai functor. And out of this, together with the theorem of Orlov, it constructs, well, in the later versions, this constructs your non-Fourier Mukai functor. Okay, so now to what we care about. So our theorem will be about T structures. So let me quickly remind you what the T structure is. So given any abelian category, well, let's start with a T structure on the derived category of an abelian category. It's an example. So you define the positive complexes to be the ones with vanishing negative cohomology, and the negative complexes to be the ones with vanishing positive cohomology. And in general, to give a T structure on it, and okay, the important thing for us about this is that if you take any complex, then you can form a truncation. So if you take any complex of in any cochain complex in an abelian category, because this is an abelian category, you can form the image of the map from y-1 to y0, and the y0 divided by this. And this permits you to express the complex y as an extension of two complexes, one of which is negative and the other is positive. So this is really the essential feature that a T structure has. And now the axiomatic description is that the T structure on a triangulated category amounts to specifying two subcategories, the negative objects and the positive objects. And they have to satisfy some axioms. So the negative objects have to be stable under shift to the left, and the positive objects have to be stable under shift to the right. There can be no maps from the shift of to the left of a negative object to the shift to a positive object. And most importantly, any object can be expressed as an extension of a negative object by a positive object. And this extension is in fact canonically unique. So both the negative part of the extension and the positive part are functorial in B, and it's common to write this truncation that way. So this is a quick reminder of what T structures are. And the theorem that we will talk about in this, okay, so we introduce some notation. The T less than or equal to n is the shift of T less than or equal to 0, and T greater than or equal to n is the shift of T greater than or equal to 0. And the T structure is bounded if, for any object, if you shift it far enough to the left, it becomes negative. If you shift it far enough to the right, it's positive. And now we come to a theorem. Well, okay. No, now we first come to the categories that will play a role in this talk. So X will be an ordinary commutative scheme. We will consider the derived category of quasi-coherent sheaves on X. If X is Noetherian, we'll consider the derived category of the bounded derived category of coherent sheaves on X. And we will also consider the category of perfect complexes on X. So remember, the perfect complexes are the ones which are locally isomorphic to bounded complexes of vector bundles. And we will also consider the relative version. So if we give an X and inside it a closed subset Z, then if there's a Z in the subscript, then it means that your complex is assumed to be acyclic when restricted to the complement of Z. So the perfect complexes supported at Z are those perfect complexes whose restriction to the complement of Z is acyclic. Okay, so these will be the categories we consider. And the talk will be about, yes, so I also mentioned that the T structure is self-dual. And the talk will be about the following conjecture. So the conjecture says that if X is a finite dimensional Noetherian scheme, then the category of perfect complexes has a bounded T structure if and only if X is regular. So let's go back a little. So to the definitions. So the category of all the bounded derived category of all quasi-coherent sheaves has an obvious T structure. The bounded derived category of coherent sheaves also has an obvious T structure. The category of perfect complexes has no obvious T structure. If you take a perfect complex, let's just assume it's a bounded complex of vector bundles, and truncate it, you will not normally expect the truncations to have resolutions by bounded resolutions by vector bundles. The truncation normally happens by taking images in some abelian category. So there's no obvious T structure. On the other hand, the theory of T structures, okay, so the theory of T structures goes back to the early 1980s. So I suppose it goes back to the period when Mumford had already left algebraic geometry. So I'm not sure a statement about this would impress Mumford, but Mumford cared about Macpherson's work on intersection homology, and the T structures came from the work of Baelins and Bernstein and Deligne, in which they gave their way of understanding perverse sheaths, so understanding the intersection cohomology of Macpherson. In any case, the one thing that was clear right from the beginning is that there are lots of T structures. After all, they give rise to perverse sheaths. So maybe I should remind you, given if your triangulated category is glued up from two others, then and you have bounded T structures on the two pieces, you can glue them to a bounded T structure on the whole triangulated category. After all, that is the way you construct perverse sheaths. They're the heart of that glued T structure. And this is all the way in the beginnings of the subject. So right from the beginning of the subject, we knew that there were exotic T structures. And in the development of the subject since then, there have been several other methods of constructing exotic T structures. So if we go forward 10 years, there's the method of Happel, Rayton, and Smaleur, who showed us how to tilt a bounded T structure to get another one. So you can tilt a bounded T structure with respect to a torsion pair. And then if you fast forward a little more, so to the work of Alonso Jeremias and Souto in 2003, they showed us how to construct T structures generated by objects. Okay, they're not automatically bounded, but they can lead to bounded T structures. And then there's the method of Harden-Riemann filtrations due to bridgeling. So you can construct a bounded T structure, in fact, a stability condition, by taking an object in your triangulated category and looking at the filtration that you obtain by forming the most destabilizing subobject. So by now we know that the world is full of techniques that build up T structures, exotic ones. So the fact that there's no obvious T structure on the bounded on the category of perfect complexes doesn't mean that there isn't one that isn't obvious. So in this context, where did this conjecture come from? Conjecture. So there's this conjecture that if X is a finite dimensional Noetherian scheme, then the category of perfect complexes only has a bounded T structure if we're in the situation where it obviously has a bounded T structure. Now, the conjecture is not due to me. The conjecture is in this paper by Antio, Gepner, and Heller. And now I should perhaps explain where this conjecture came from. So this is a beautiful paper, which I'll say a tiny bit about. So what did Antio, Gepner, and Heller prove in this paper? So they show that if T, okay, suppose you start with a model category. So for us, a model category can be either a DG category or an A infinity, I don't care. Any model category you wish to have. Then you can define its K theory, and in particular, its negative K theory. And the theorem says that if the homotopy category of M, okay, you start with a model category M with homotopy category T. If the homotopy category T has a bounded T structure, then K minus 1 of M has to vanish unconditionally. And all of the negative K theory of M has to vanish if the heart is Noetherian. So if you think of it as a vanishing theorem in negative K-theory, it generalizes an older theorem of Schlichting. But this is not the way we want to think of it today. Today, we want to think of it as an obstruction to the vanishing of T structures, to the existence of bounded T structures. I mean, one of the things this theorem tells you is it gives you a way to show that a category cannot possibly have a bounded T structure. So as a corollary of this theorem, if X is a finite dimensional Noetherian scheme, if K minus 1 of X is non-zero, then the category of perfect complexes on X cannot have a T structure. And if Kn of X vanishes, is non-zero for n less than or equal to -2, then any bounded T structure on the perfect complexes cannot possibly have an Noetherian halt. So there are many examples of X's with non-vanishing negative K-theory. All of them are singular. It's known that if X is regular, then the negative K-theory has to vanish. So based on that, being courageous, Antiochepner and Heller conjectured that, so this corollary is in the paper by Antiochepner and Heller, and they formulated the conjecture. Hey, why not conjecture that the category of perfect complexes only has a bounded T structure when it has an obvious bounded T structure. So this is a brave conjecture. Remember, there's there was K-theoretic evidence for it, but the K-theoretic evidence is well short of the statement. There are many singular schemes for which the negative K-theory vanishes. Well, sometimes brave conjectures are true, and as it happens, this conjecture is very true. So the theorem is that if X is any Noetherian scheme, and Z contained in X is any closed subset, then the category of perfect complexes on X, which are acyclic outside Z, has a bounded T structure if and only if Z is contained in the regular locus of X. So this turns out to be a theorem. And what I want to emphasize today is that the proof of the theorem is very much using the techniques of non-commutative algebraic geometry. It's very much using the work of Van den Bergh. So I'll try to sketch the main idea of the proof. And I'll try to do it in a way that simplifies things. After all, we're trying to impress the modern equivalent of Mumford. We are trying to show that this is an interesting theorem, even if you just restrict the projective varieties. So most of the time, I will not worry about, the theorem is true in this generality. I've stated it, it's true like that. But I will assume that X is actually a projective variety in much of the proof, and show you, one, that the theorem is already interesting there, and two, I will try to give you an idea of how the proof goes in the simple case. So the proof may be found in the preprint here, and now here's the idea. It suffices to show that the inclusion of the perfect complexes in the bounded derived category of coherent sheaves is an equivalence. So Okay, so let's go slow. If this inclusion is an equivalence, this inclusion is an equivalence if and only if Z is contained in the regular locus. Now, the category on the right obviously has a bounded T structure. So what we have to show is that if the category on the left has a bounded T structure, the inclusion is an equivalence. So how do we show this? Well, we want to take an arbitrary F, which is a bounded complex of coherent sheaves. We are assuming that the category of perfect complexes has a bounded T structure. And somehow we want to show that from this, we can deduce that the F actually has to be a perfect complex. So what is the idea? Well, so the idea is the following. And remember, I'm assuming for simplicity that X is a projective variety. So X is a projective variety. It has enough vector bundles. So take our object F. It's a bounded complex of coherent sheaves. You can form a resolution by vector bundles. You can always resolve it by vector bundles. Now, whenever you resolve it by vector bundles, there is the brutal truncation. So the brutal truncation gives you a distinguished triangle. And this distinguished triangle, I mean, you can take M to be minus 5 million. You can always do this. And this produces for you an exact triangle, which I'll write as D goes to E goes to F, where E is some perfect complex, and D can be as negative as you want. After all, I can choose M arbitrarily. Now, okay, so we have proved the existence of such triangles as long as X has the resolution property. Now, the existence of such a triangle, if X doesn't have the resolution property, uses the ideas of Bundle and Vandenberg, and it was done in a paper by Lippmann and myself in 2007. And actually, we will need the relative version. So we will need the version where X is a scheme and Z is a closed subset. And that came later. That can be found in the stacks project. So you see, it already isn't obvious that if you want, that you can do it. You can take an F, which is a bounded complex of coherent sheaves whose cohomology is supported on Z, and resolve it by a perfect complex supported on Z in such a way that the third edge of the triangle is also, well, the third edge of the triangle has to be supported on Z. So this isn't obvious even if you're in the projective case, meaning even if you have enough vector bundles. It needs proof. And it turns out that this proof uses the techniques of Bondar and Vandenberg from the 2003 paper. So it's in the stacks project, it's been done, but it appeals to the techniques of non-commutative algebraic geometry. Now, okay, so given any object F, which we, for simplicity will assume has cohomology only in positive degrees, you can always find a perfect complex and a map from E to F so that the triangle D goes to E goes to F has D as negative as you want, minus 15 million. So the cohomology vanishes. The ordinary cohomology, sheaf cohomology of this complex E vanishes in degrees between minus 5 million and 0. There's a very big gap in the cohomology. Now remember, with respect to any T structure, you can truncate. After all, T structures allow you to truncate. And if you take the truncation in the boundary-derived category of coherent sheaves, then there's going to be an enormous range between -5 million and 0, where the truncation agrees with E goes to E goes to F. So now we are assuming that there's a bounded T structure on the category of perfect complexes, and E is a perfect complex. So in order to prove our theorem, it suffices to show that the bounded T structure on the perfect complexes is such that it's not too far away from the ordinary bounded T structure on the boundary-derived category of the coherent sheaves. What we really want to know is that truncating in the category of perfect complexes will give us this triangle, because that will force F to be a perfect complex. So what we really want to measure is the distance between the bounded T structure on the perfect complexes and the obvious bounded T structure on the boundary-derived category of coherent sheaves. So this is best done in some other category, and it's best done in the category of. So we have to define the distance. So we define two T structures to be equivalent if they're not too far apart from each other. So we need to show that the bounded T structure on the perfect complexes is equivalent to the ordinary bounded T structure on coherent sheaves. And it's best to do this in a category where both T structures exist. And the easiest is to do it in the category of quasi-coherent sheaves supported in Z. And so somehow we have to compare T structures. And fortunately, so there's a theorem by Alonso, Jeremias, and Souto which allows us to do it. So given any T structure on a small category, you can look at the T structure it generates on some larger category. So in the category of quasi-coherent sheaves, we can actually do a comparison of the two T structures. But then something needs to be proved. So, okay. So the theorem of Alonso, Jeremias, and Souto says that if you let A be a set of compact objects, for example, you let it, then it generates a T structure. And for us, we're going to take A to be the set of negative perfect complexes with respect to our T structure. So A is, we are given a T structure on the derived category of perfect complexes. We let A be the negative part of this structure. And then we take the T structure this generates on the unbounded derived category of quasi-coherent sheaves. And we want to compare this. Okay, so this is technicalities. We want to compare this to the standard T structure on the unbounded derived category of quasi-coherent sheaves. So we have to prove something. And for example, we have to prove that the less than or equal to 0 part of the usual T structure on the unbounded derived category of quasi-coherent sheaves is contained in some shift of the less than or equal to 0 part of the T structure generated by it. So I went through this fast. Are there any questions? Okay, so what is the key idea here? So again, I'll explain the key idea, assuming that X is a projective variety. So suppose we take an object in the unbounded derived category of quasi-coherent sheaves, which is negative. So we can resolve it. So it's a complex of quasi-coherent sheaves, which ends at 0. We can resolve it, okay, now by infinite vector bundles. So the VI are no longer finite rank vector bundles, they're vector bundles of arbitrary rank, but we can make them direct sums of shifts, direct sums of twists of O of 1. In fact, we can assume that of the form direct sum of O of minus L, where L is possible. Okay, so any object in the unbounded derived category of quasi-coherent sheaves on X has such a resolution. Now, we are given a bounded T structure on the perfect complexes, and A was declared to be D less than or equal to 0. So this is a bounded T structure, which means that A less than or equal to 0 will contain the shift of any perfect complex. Of course, the shift depends on the perfect complex. So if you take O of minus L, it's going to be contained in some shift of A. Unfortunately, the shift depends on L. So if I take any finite collection of O of minus L's, I can find some shift of A that contains them all. But I can't, I mean, the resolution here involves infinitely many O of minus L's. So how can I get around this problem? How can I somehow show that if I shift A to the left enough, it will contain all of the O of minus L. So now we come to the theorem of Bondel and Vandenberg, which shows that there's a single compact generator. And actually, I'll use an improvement due to Orloff. So the improvement due to Orloff is actually best illustrated this way. So you take any commutative ring and look at this dumb complex. So R is resolved by multiplication by X from R of X to R of X. And you tensor this with itself many times. And when you apply Prudge to this, you discover that O of 1 has a resolution by O of L, where all of the maps are linear. So in degree 0, you get direct sums of O. In degree -1, you get direct sums of O of -1. And going all the way down to O of -8. So O of 1 has a resolution. It's given by the Koszul complex. Okay. Now tensor this with itself L times. So this actually is essentially an argument. I say this follows an idea of Orloff's. Take this and tensor it with itself L times. Then you get a resolution for O of L, where again, all of the maps are linear. So in degree 0, you just get direct sums of O. In degree -1, you get direct sums of O of -1, and so on. Of course, the resolution gets longer and longer as you take this complex and transfer it itself L times. As L grows, so will the resolution. But you can truncate this resolution. You can truncate it in degree -n. Just take the brutal truncation. So this now is a complex of 3 modules. It has cohomology in degree 0 and cohomology in degree -n. In degree 0, we get a vector bundle, O of L. And in degree -L, we have to get the vector bundle. I have no idea what vector bundle I get, but I get some vector bundle. I don't care. So this is an extension of O of -L by some vector bundle L. So it's an element in X to N, Xn plus 1, of O of L or by some vector bundle. And that X group is 0. So this complex has to be the direct sum of O of L with some nonsense. Who cares about the nonsense? And now you apply the dual functor to it, and you get a dual complex, which involves O of 1 up to O of n, and it's isomorphic to O of -L plus some nonsense. Who cares? So now the point is that as long as A of -n contains O of 1 shifted 1 to the right, O of 2 shifted 2 to the right, up to O of n shifted n to the right, it has to contain O of -L for every L. That means we're done. The entire resolution lies in the subcategory generated by A of -n. So that proves it. Okay, so that plus a little bit of fiddling proves the theory. Okay, so I gave you a proof that's true for projective varieties. If you want to generalize, if you want to generalize to other varieties, you have to use deeper techniques in the paper by Vondel and van den Bergh. It works. So you can even do a relative version. Let me not go into this. So, but I should say just epsilon, so the techniques are useful elsewhere. And yes, and all of these, I give you some literature on this, and I should probably stop here. Thank you very much.